Hello, this is the video for Unit 1 Limits and Continuity from AP Calculus AB and BC. Now, let's try our hand at some problems. So here are a whole bunch, 4 problems. Okay. Now, this is how limits will usually be presented to you on the AP exam. They'll say lim, and then they'll say as x approaches to, what is the value of this function? And you can just sit there and take neg 2 and plug it in. Right? So if you plug it in there into this first question, you get 2 squared, 4, minus 4 over 2 squared, 4, plus 4, which, well, the numerator is 0, so this whole function is just going to be 0. So therefore, B is the correct answer there. All right, let's see another one. Now they're asking for the limit as x approaches infinity. Limits approaching infinity. Now with limits approaching infinity, you can't just plug it in, right? You can't just plug in the value of infinity because, well, what do you get? You get 4 minus infinity over infinity minus 1. And how do these infinities compare to each other? We don't know. So the way to do these kinds of problems, let's see, let's order the numerator in terms of the highest degree power is x squared plus 4. And then on the denominator, we have x squared minus 1. Now imagine if we were to divide the numerator by x squared and the denominator by x squared. Now remember, we're doing the same thing to both the numerator and the denominator, so we're not changing anything, right? This is still the same fraction. If we divide the minus x squared term by x squared, we would end up with just negative 1. And then plus 4, and then that would be over x squared. And so it would be plus 4 over x squared. And then this x squared term right here, this would be, instead of being x squared, when we divide by x squared, it's just going to become 1. And then this minus 1 over here is going to become minus 1 over x squared. Now you might not see what we've done. You might not see how this helps. But now let's try plugging in infinity and see what we get. Now if we plug in infinity into this whole thing, we get minus 1 plus 4 over infinity. 4 over infinity. Well, as infinity grows to infinity, it just becomes really, really large. So 4 over infinity becomes really, really small. And as x approaches infinity, 4 over x squared approaches 0. So in essence, when we're plugging in values of infinity into a limit, we can just cross this out because it's over infinity. The same goes for the denominator. And now all we're left with is minus 1 over 1, which is equal to minus 1. So C is the answer. And this concept will hold with any limit going to infinity. Right? How you can think about it is if the degree of the numerator is bigger than the degree of the denominator, right? Let's say what can we do? Let's say x squared plus 1 over x plus 1. And then we do the same thing where we divide both sides by x squared, and we end up with 1 plus 1 over x squared. And then we divide that by, well, 1 over x plus 1 over x squared. And you can look at that, and you see that if we were to plug infinity into this, then this cancels out. This here right here cancels out. This right here cancels. And then this cancels. So basically just left with 1 over 0 at this point. Now 1 over 0 is not, it's not defined. But remember, this isn't just 1 over 0. This is 1 over something approaching 0. It's getting very, very, very tiny. Right? So as this gets very, very, very tiny and this stays at basically 1, what's 1 over something very tiny? Well, that equals infinity. Right? If in general, if you have a limit where the degree of the numerator is bigger than the degree of the denominator, your limit will be equal to infinity at a limit going to infinity. And you apply the same concept with limits going to negative infinity. The signs are obviously going to change, but it's the same idea. And then if you have limits where the degree equals each other, right, with here, highest degree is 2, the denominator, the highest degree is 2, then it's just going to be the quotient of the coefficients. The coefficient of x squared in the numerator is negative 1. The coefficient of the x squared in the denominator is positive 1. That equals negative 1. So our answer was negative 1. And then for the last case, where the degree of your denominator is lower than the degree of your numerator, when the degree of your numerator is lower than the degree of the denominator, when you have something like x plus 1 over x squared plus 1, well, if we were to apply the same thing again, I'm not going to write it because we've written it like 3 times already, then this numerator divided by x squared is going to go to 0 because it's going to be 1 over x plus 1 over x squared. And when you're dividing by infinity, so that's just going to be 0. So this is just like saying 0 over, well, this is going to be like 1, right? Because this plus 1 cancels out because it's over infinity, but the x squared divided by x squared becomes 1. So we just end up with 0 over 1, or 0. So, summarizing all this up, if the degree of your numerator is bigger than the degree of the denominator, the limit at infinity is going to be infinity. If your degree of the numerator is equal to the degree of the denominator, the limit at infinity is going to be the quotient of their coefficients of the highest degree terms. And if the degree of the numerator is smaller than the degree of the denominator, your limit at infinity is 0. Now with all that said, let us finally get on to another question. Now, here we can just see, let's just plug in the values, right? So we have 3 minus 3. Well, that equals 0. Let's look at our denominator. X squared, that's 9, because 3 squared is 9, minus 2x, so minus 6. 9 minus 6 is 3. 3 minus 3 is 0. So it would look like your answer is 0 over 0. But this is not a valid limit, right? We call this an indeterminate form. And what that means is that this form is not complete, right? Now let's see what we can do about this. Now what we can see is that, well, we can factor out the denominator, right? We can say this is x plus 3 over, x minus 3. X minus 3 over, factoring the denominator, we get x minus 3 times x plus 1. And you might just jump to, well, let's just cancel these x plus 3's out, right? We have one in the denominator, we have one in the numerator. Let's just get rid of it. And then you end up with 1 over x plus 1. And it makes sense, right? When you just cross out the factors, the numerator denominator, and you just get 1 over x plus 1. And this is a valid way to do it. Now just notice that this is not the same function, right? Because at x equals 3, if you were to plug this into that function without the limit, it would be undefined. If you were to plug this into this function, you would get 1 over 4. So they are different functions, but just barely. If you notice that anything other than x equals 3, we can divide out this x minus 3. Because at x equals 3, this term is going to be 0. We can't divide that out. At anything other than x equals 3, then this term and this term will both not be 0, so we can divide them out. So this is our function for everywhere except x equals 3. And remember, our limit is not our exact value. So we get when we approach it. So as we approach 3, we can use that function that's circled. And since we're just asked for the limit, we can plug this x equals 3 into this limit, and we get 1/4. And that is our limit. Therefore, our answer is C. Right, that was long. Let's see what we have with some more problems. Let's take these two. Now these two are less of calculating limits and more about thinking about conceptually what is going on with limits. Now let's see. First question, the graph of y equals the arctangent, the inverse tangent of x has. And they say vertical asymptotes at x equals 0 and x equals pi, horizontal asymptotes at y equals plus or minus pi over 2, more horizontal asymptotes, more vertical asymptotes. So now we have to decide, well, which of these is true? Now, let's see. Do we have vertical asymptotes at x equals 0 and x equals pi? Let's see if we can verify that. Well, at x equals 0, arctan x is arctan x. Let's write it like this. Arctan x equals y. If we write it like that, we can take the tangent of both sides, and we just get x equals the tangent of y. And now we can just plug in these values. Right, so if x equals 0, then y has to equal, well, let's see, if we put in 0, radians, because remember tan is sine over cosine, then the sine will be 0. So at x equals 0, y is also 0. It doesn't, a vertical asymptote would have like dotted lines, and the two values of the curve would be like curving up. Like, let me attempt to draw a graph of it. If this is your line, like say x equals 0, which it's not because we've just verified that it's not, but if it was, then a vertical asymptote would look like this. It would go up, and it would never actually cross that line on this side. It would keep going up to infinity. And then maybe you'd have the other one over here, maybe be going down. It doesn't have to be going down, or it could be going down like this, but it also could be going up. But that's what a horizontal asymptote means. And as you can see, tan y is not a horizontal asymptote, because at a horizontal asymptote, this would be undefined. And it's not undefined, it is defined. It's 0, y equals 0. Now we can, so since x equals 0 doesn't work, we can just cross that answer out. Right, that answer does not work. Now we can look at answer choice B. Yeah, the graph of y equals arctan x has horizontal asymptotes at y equals plus or minus pi over 2. Alright, now what do horizontal asymptotes mean? Horizontal asymptotes. Remember what we saw in the last problem where we had the limit on infinity? Those are what horizontal asymptote means. Alright, now let me pull back one of those questions. Just to see. For this second question right here, we would have a horizontal asymptote at y equals -1. And all a horizontal asymptote means like this limit when it goes to infinity. Right? Because as it goes to infinity, everything flattens towards that line, and that becomes your asymptote. That is all that means. Now, do we get that line at pi over 2 and negative pi over 2? Well, as we go to infinity, as we take the arctangent of infinity, we get really close to what? Well, let's see. If we take the arctangent of x, do we get close to pi over 2? If we take the arctangent of infinity, so that's like saying tan y equals infinity, then y is going to be approaching something like pi over 2, right? Because if you think about it in terms of the sine y over cosine y, as we approach pi over 2, sine y becomes 1, and cosine y becomes 0. It's like 1 over 0 again. And that takes us near to infinity. So that would at putting y equals pi over 2 would take x to infinity. In other words, if we put x at infinity, we get y equals pi over 2. Now this also works for y equals negative pi over 2. Now remember that if we plug in negative pi over 2 into tan y, sine y now approaches negative 1, and cosine y now approaches 0. So that would be negative infinity. So in essence, what we're seeing is that as we approach negative infinity in x, we approach minus pi over 2. And as we approach positive infinity, we approach pi over 2. Right? So these are horizontal asymptotes. So B is looking correct. But just to be sure, let's go through all the answer choices. Let's look at C. Horizontal asymptotes at y equals 0 and y equals pi. Well, at y equals 0, right? Let's put this back. X equals tan y and y. If we put in 0 for tan, we get x is 0, right? Because tan y is just the sine over cosine. Sine is 0, cosine is not 0, so it's x becomes 0. If we plug in y equals pi, we get the same thing. Sine is 0, cosine is not, it's negative 1. So that just becomes x equals 0. So those are not horizontal asymptotes. So this one, C, does not work. Now let's look at answer choice D. At x equals plus or minus pi over 2, they're saying we have vertical asymptotes. So basically, y is not defined at x equals pi plus or minus pi over 2. Well, so we have to have tan y equals pi over 2. Now there's really no reason why tan y couldn't equal pi over 2, right? Or negative pi over 2, right? And remember, the tangent function has essentially no limit, right? It can be as big or small as possible, right? It can go down to 0, it can go up to infinity or negative infinity. There is no limit. There's just its domain is infinite. Its range is infinite. Sorry. So pi over 2 and minus pi over 2 are both going to be defined for y. Therefore, you're not going to end up with vertical asymptotes. So, like we thought before, our answer here is B. Let's move on to the next question, see what we have. The graph of y equals x squared minus 9 over 3x minus 9. And they're basically asking us the same kind of question, right? Does it have vertical asymptote? Where? Horizontal asymptote? Where? But then they have these two other things. They have removable discontinuities and infinite discontinuities. Now let's figure out what those mean. A removable discontinuity is basically a point on the graph where you have a hole. Let me show you. Using this graph from 4, at x equals minus 3 we have a removable discontinuity, right? It's a hole in the graph. Right? If we take that hole out, then the graph will be continuous. We're just going to ignore this other point right here because it's not part of the curve. If we take this point out, the curve is continuous. It's a removable discontinuity. Now, an infinite discontinuity, I don't have one, but this is what it looks like. It's basically a vertical asymptote, right? You have this vertical asymptote, and then you have this line, and it goes up to it really close, but never actually touches it. I know it looks like it touches it, but infinite discontinuity doesn't actually touch that line. And the same thing on the negative side, doesn't actually touch the line, but it gets really close. That's what an infinite discontinuity is. It's essentially the same thing as a vertical asymptote. And that might prompt you to just, well, you can't have two right answers and just cross them all out. And let's see if that is true. The graph of y equals x squared minus 9 over 3x minus 9. Now, one thing we can notice is that at x equals 3, this function is undefined. It's the only value where it's undefined, right? So at x equals 3, well, we can factor that out. We can factor x minus 3 times x plus 3 over 3 times x minus 3. And then we can just cross these out and say that at everywhere except x equals 3, the function is just x plus 3 over 3. Now let's look at our answer choices. At x equals 3, do we have a vertical asymptote? Well, when we have x minus in the denominator, we usually have a vertical asymptote. But here we don't, because here we also have an x minus 3 term in the numerator. So when we cancel these out, we just get x plus 3 over 3. So we'd end up with just a linear function like this, except that at x equals 3, we'd have a hole in there. And that is a removable discontinuity, right? As you can see, it's a discontinuity, right? We obviously can't. We obviously do not have a value for y at x equals 3, but also we can just remove it. We can just remove the term from both sides, and now we have a function. And it's defined at 3 now, right? So we removed it, and now the function is defined. Now the function is continuous. Now we can see that D and A are both not correct because you don't end up with that like line going to infinity, you just end up with a hole. So these two are incorrect. And I think it's pretty obvious that C is the correct answer now, but we can check it out just to be sure. Now remember from before that how to evaluate limits at infinity, right? Now the degree of the numerator is 2. The degree of the denominator is 1. The degree of the numerator is bigger than the degree of the denominator. So the limit is infinity. This function goes to infinity. Therefore, this is not correct. It does not have a horizontal asymptote. The function does not go to one value. The only time you would have a horizontal asymptote in this kind of scenario is if the degree was the same, but it's not, so you don't have that. Therefore, the answer to this question is C. So with that, let's get on, see if we have another problem set to do. Here we have one that focuses pretty heavily on our definition of continuity. Now we get to practice continuity. So, let's see, which of the following statements are true or is true for this function? And we're given these options and we're asked, like, is it one only, two only, is it two of them, is it all of them? And let's see what we have. At x equals 0, at f equals 0, we use this bottom function, and it's 1, right? So this is just at f of 0 is 1, right? So this one exists. This is true. Therefore, well, the answer can't be B because it doesn't have 1 in it. It has to be one of these three. The limit of f of x exists. Well, if we approach from both sides of x equals 0, right, do we have a value, right? It's not about this if x equals 0 statement, right? This doesn't matter at all because, well, it doesn't matter because we're not concerned with the actual value when we're discussing the limit. We're concerned about values around it. Now, looking at this top function, we can see that we can factor the x out, and we get x plus 1. Pretty simple function. Well, as you approach 0, this is a polynomial, which means it's defined everywhere, and it's always continuous. So this polynomial, the limit will exist, right? As you approach 0, this thing approaches 1 from both sides, right? It's literally just a line, right? It's going to approach from both sides. So therefore, 2 is also correct, so it can't be A. And now we look at the last one. F is continuous at x equals 0. Now, thinking about our definitions of continuity, right? Let's see this up here. You need all three of these criteria to be satisfied for something to be continuous. We got that f of a is defined, right? We got that the limit exists. Now we have to see that they both equal each other. The limit at x equals 0 is, we just plug 0 into this polynomial over here, and we get 0 plus 1 equals 1. The limit is 1. F of 0 is also 1, right? If x equals 0, it's 1. 1 equals 1, so that means that the limit and the value are equal. The third criteria is satisfied, so this is continuous. So all three of these conditions are true, and the answer is D. Right? That was a good application of continuity. And now, let's see if we have any more problem sets. We have these couple more questions. We have this function up here, suppose that it's a piecewise function, right? It's defined at f equals 1, it's this, at f equals 2, it's that, and we have this for everything else. And we're asked, is f continuous? Where is f of x continuous? Right? And we know that it's continuous at everywhere except 1 or 2, because it's just one function for those, right? And for those, the denominator is not 0. So everywhere except for 1 or 2, it's continuous, right? So it has to be one of these answer choices. Now we can see, is it continuous at 1? Is it continuous at 2? And let's look at what we can do with that. Well, the first thing we see is that this x squared minus 3x plus 2, we can factor that and make x minus 2 times x minus 1. And that the denominator, this 3x times x minus 1, we can remove this term, we can get rid of that term, and we end up with 3x over x minus 2. Alright, so let's look at x equals 1 first. At x equals 1, the value it's defined as negative 3. The limit as we approach 1 is going to be the value of this function when we plug in 1. We plug in 1, 3 times 1, 3 over 1 minus 2 minus 1. 3 over minus 1 is 3. The limit does exist, and the limit is equal, right? The limit minus 3 is equal to 3. They are equal, right? So at x equals 1, this function is continuous, right? So that means that this one is wrong, this interest is wrong, and this interest is wrong. Now let's move on to 2. At f equals 2 is 4. It's defined. At if x equals 2, well, if we plug that in here, we get 6 over 0. That doesn't work, because 6 over 0 would give us a vertical asymptote, right? If we have something in both the numerator and denominator, we get a removable discontinuity. If we have a number over 0, we end up with a vertical asymptote. If we have 0 over 0, that's different. Right? Then you have a removable discontinuity, most likely. That's indeterminate form. You can't decide anything from that. Here you have a number over 0. That gives you a vertical asymptote, meaning that the limit doesn't exist. So the function can't be continuous at x equals 2 because it violated one of our 3 criteria. So the function is not continuous at 2, and B is our answer. It's continuous everywhere except at x equals 2. Now let's look at this next question. The graph of f of x equals 4 over x squared minus 1 has one vertical asymptote, the y-axis as its vertical asymptote, the x-axis as its horizontal asymptote, and plus or minus 1 as its vertical asymptotes, and 2 vertical asymptotes, but no horizontal asymptote. Alright, now obviously we're not just going to go through our answer choices because that seems really tiring. We're going to actually try to figure out our horizontal and vertical asymptotes. Let's look at this. We have 4 over x squared minus 1. Let's look at vertical asymptotes. Vertical asymptotes, the numerator is a number. Well, it's already a number, it's 4. The denominator is 0. If we can make the denominator 0, we have vertical asymptotes. We can make the denominator 0 with x equals 1, right? 1 squared minus 1, that's 0. Or negative 1. Negative 1 squared is 1, minus 1 is also 0. So we have 2 vertical asymptotes as positive 1 and minus 1, or plus or minus 1. So it has to be either C or D. It can't be B, and it can't be A, and it can't be B, because they don't talk about this, right? They say they have vertical asymptotes, and they say they have it at, well, y-axis is x equals 0, and here's x equals 1. They leave out this minus 1, and they leave out the positive 1. Looking at C, this says x-axis adds horizontal asymptote. This one says no horizontal asymptote. Now, if the degree of the numerator is smaller than the degree of the denominator, you're going to end up at 0. When you get really big, you're going to end up at 0, meaning that you do have a horizontal asymptote. It's at 0, because as you go to infinity in both directions, you're just going to end up at 0. So you have y equals 0 as your horizontal asymptote. And y equals 0 is the same thing as saying the x-axis. So the x-axis is a horizontal asymptote of this function. So the answer is C. Now that's all of our problems. I hope you enjoyed this video. I hope you learned something from it. And if so, I'll see you next time.